Hello. In this video, I would like to demonstrate how you go about plotting the frontal system associated with thunderstorms and how you can use Stuve diagrams to actually forecast where thunderstorms are most likely to occur. Okay, so first of all, let's get to the frontal system and let me explain how you go about actually plotting this frontal system. All right, so the first thing that you want to look at is you always want to go and you want to plot your low pressure center. Okay, and so as you know, as I've provided instructions on how to do this, here's what I'm going to actually look for. My low pressure center is right in this area. And the reason that I've, concluded that it's right in this area is the first thing is you notice that you're always going to look for cloud cover and of course the most extensive cloud cover that you can find. And so with that, I notice that right in this area I see extensive cloud cover. Okay, and now what I'm looking at is notice how you've got the counterclockwise rotation. You can see the actual winds are coming from this direction and then they go counterclockwise like this. So by looking at all these wind directions, that's how I've come to conclude that this is where the low pressure center is at. Now, after I look at that, there is one last thing I'm going to look at, and I'm going to look at, I see 996.2, 996.6. So that's why I moved it over a little bit as compared to 997.9. Okay, now the one thing that students do not tend to use is they do not tend to use the wind directions as also help on where you're actually doing this. Okay, notice how these wind directions are coming like this, and so what that does is that gives me a heads up about not only where the low pressure center is, but it's also going to give me a heads up on where the actual frontal system is located. Okay, now the habit with myself is I always do the low pressure center next, and of course you realize that it kind of hinges right there at the low pressure. So what I'm going to do is I'm going to go ahead and I'm going to start moving this around to depict where I want it to actually go. Okay, and so I'll continue to do this and move it around, and what I've come to find is I'm going to go a little bit farther. Okay, and so what we have here is I have the cold front. And how I actually determine the location of the cold front is what I always use temperatures as my divider, but then I also use wind directions. You notice that back here most of the winds are coming from the north, so this is your continental polar air mass in this area, so that kind of gives me the heads up there. And then what I see down here is I see winds coming from the south-southwest, and so that actually kind of gives me one of those variables that I can actually look at to kind of help me determine where that low pressure center is. Now the next thing I'm going to do is I'm going to go ahead and move my warm front over here as well, and then I'm going to start manipulating it. And one thing you have to remember is whenever you're doing these frontal systems is whatever side these symbols are on, that indicates the direction that the air mass is actually moving. Okay, so this continental polar air mass is actually moving in this direction, whereas the maritime tropical is actually moving in this direction. Now, with this, what I'm going to start to do is you're going to start to notice how you see that 54 and that 32. That's kind of one of those dead giveaways. I'll have to manipulate it a little bit more, flatten it out a little bit. And again, you're just trying to, in a sense, get relatively close there. And so there's what we're actually looking at. Now, what did I use to actually locate this? What I used is I used the temperature, of course, but I also used the wind direction. Okay, wind direction actually is one of those major dividers for me to actually say, okay, this is what's actually going on there. Now, I will say that this one can go a little bit more because I see that 34 in that back there. Notice how I hinge them right at the low. Oops. There we go. Okay, so now I've got it hinged right there. So you see all these cold temperatures are behind. 48 is kind of like the halfway in between, and that's why that frontal system is running right over that right now. And then the last thing that I want to look at is I start to notice, whoa, wait a second here. I see winds coming from the west and this, and notice how dry this air is. That's 26 degrees of difference between those, whereas these are close. And so whenever you see something like that, that right there is a dead giveaway of a dry line. Okay, so now there's my dry line right in that actual area. Okay, so this is what we're actually looking at, and now we've got our frontal systems actually set up. Now, whenever we start looking at these maps and everything, and we start to say, okay, now we're going to use these to forecast the weather and what's going on, what we're trying to do is we're trying to determine which actual city. We've got 4 cities. We've got Topeka, Kansas, Springfield, Missouri, and Topeka's out here. Okay, Springfield, Missouri, right there. We have Nashville, Tennessee, which is right there. And then we have Shreveport, Louisiana, which is right here. Okay, so now whenever you start looking at the chances of thunderstorms, right now I can see that there's really only 3 cities that have any concern: Springfield, Shreveport, and Nashville. Okay, and the reason that they have this concern for possible thunderstorms is because you have a lifting mechanism right out there coming, and that would be the cold front in this situation, and then the dry line down in here for Shreveport. And so whenever you look at how this low pressure center is going to move, you have to remember it goes with the upper level wind systems, so it's going to be traveling in this direction. Okay, so that cold front is going to be, or excuse me, that low pressure system as a whole will actually be moving this way. That cold front moves a lot faster than the warm front, so it'll eventually catch up and occlude off once it reaches and kind of closes up. You know, that with the warm front, you get an occluded front. So that'll probably happen somewhere up around in New York, Vermont, that New Hampshire area, possibly even as far up as Maine, that you'll start to see it occlude out. Okay, now, so what you want to do is now the next thing you have to say is I have to look at these and say, okay, so which city's at the greatest risk? We've already narrowed it down because look, Topeka is behind the cold front, so the weather has already passed Topeka. Okay, so if we start looking at it, here's Topeka right there. You notice what you see is, yes, you do see some surface thing there, surface moisture, because it's very moist at the surface. But what you notice is you have exceptionally dry air, but I'm focusing on the parcel right here. Okay, so if you look at that parcel, the parcel is to the left of the actual temperature line. So this is the parcel line, this is the environmental lapse rate line. And so whenever you start looking at this, you start to say this parcel is to the left. That's a dead indication of stability. Okay, and so nothing is going to happen in Topeka, Kansas. All right, let's go over here, and this right here is Nashville. Okay, so looking at Nashville, you can say right now, look at the relationship between each one of these. Now, of course, you could go through and you could use the lifted index calculations or the totals would actually be a good calculation. And so you could do the lifted index or the totals, but I'm really just using I'm just using the temperature and the parcel line, okay, right now. And right now I'm seeing that Nashville is actually kind of stable. Now, can that change? It could, but most likely it's not going to change significant. So I wouldn't say that there would be severe weather, the chance of like severe thunderstorms occurring in Nashville. So we've narrowed that down. So now let's go to somewhere. This right here is Shreveport, Louisiana. And what I know now is I'm starting to look up here and I start to see that we have moist air at the surface. Once that crosses over, we have that right there at about 3,000 meters, 3 kilometers. We have the level of free convection, and notice how far it is away to the right. Let's take a look at Springfield. Springfield is kind of the same. So because of this, what you can actually look at is you can say, okay, there are these 2 cities that are at risk for severe weather. And now if you start looking at it, you can see that the frontal system is approaching in Springfield, so you're probably going to have thunderstorms occurring there much sooner than you will in Shreveport, Louisiana. But here's what you have to look at. Because the cold front is advancing here, and you can see, let's see what the temperature and the dew point are with these. Okay, so you're looking at 20 degrees Celsius. That's about 68 degrees. And the dew point is at about 67 degrees roughly. Okay, and so it is relatively moist, but not too bad. That's actually probably closer to 65 degrees. Okay, you notice that it's very, very wet right there. So that's what you're looking at there. Let's go ahead and go up to Springfield. Springfield is actually about the same. But you'll notice is what you have here in Springfield, you do have a little bit of a cap that can actually provide some severe thunderstorm, because that cap on the atmosphere is kind of letting it boil up. Let's go back here. No cap here. But the one thing that you want to look at is you want to go to the 500 millibar level and look at that gap. And this is where I would do my lifted index and totals calculations. And then once you actually do the lifted index and totals and you look at that spacing in between there, you can actually see that Shreveport is at a much higher risk than Springfield. Okay, something else that you would look at here, and you'll see this coming over there. You can see that in Springfield, yeah, we do have some southwest winds, and then you go vertical here. It stays southwest, and then it goes a little bit to southwest, or excuse me, west southwest, and you can see there's not a lot of what we call vertical wind shear. But look here, look at how that wind changes with height. That right there is a sign of vertical wind shear, and that right there is a great indication of possible tornadic development. So this over here is one of the key things that I would actually look at. Now, whenever you start looking at this, let's see what we got here. Another way you can actually do it is look at the right here's the measurements on all the side, in case you didn't know that. There's your totals. Your totals is 58. Your totals in Springfield is 56. Okay, so automatically you can see the answers are actually right there, that Shreveport is actually at a greater risk of severe weather. And so that's how you go about using all of these different variables to actually determine which cities are going to have thunderstorms and which cities are going to be at greatest risk of severe weather. And so that's how you can use your weather map and your Stuve diagrams for this. Now, one thing I want to note, the reason that I'm using Stuves and not something called SKUTs is because I think that Stuves are easier to read for beginning students, because everything is kind of like laid out, and it's really a lot simpler to read. So, but I will tell you that most meteorologists actually use a diagram, what is called the SKUT. There's just a lot more slanting to it, and so I just try to keep it simple by using these actual Stuve diagrams. So hopefully this explains how we go about determining which atmospheres are the least or most unstable, and how you go about determining the possibility of severe weather.